In this lecture, we'll discuss how to handle special combinations of multiple resistors that frequently show up in the analysis of circuits. You'll recall that in an earlier lecture, we discussed how we could analyze this single loop circuit with a single resistor using the loop rule, where Ohm's law could be used to relate the magnitude of the potential difference across the resistor to the conventional current capital I and the resistance capital R of the resistor. Let's look at this example where we have two resistors, one after another in a single loop circuit. This one after another structure is described as two resistors in series. We can apply the loop rule to obtain this expression, and again we could use Ohm's law to relate the potential differences across each resistor to its resistance and current capital I. However, there's a nice technique that allows us to replace these two resistors in series with a single resistor that is electrically equivalent. So let's discuss how that works. So here we have two resistors, R1 and R2, in series, and we want to replace this combination with a single equivalent resistor, REQ, like this. Just to be clear, replace will mean that the potential difference across REQ will have the same magnitude as the total, the sum of the potential differences across both of the original resistors. We can use Ohm's law to describe these potential differences, and notice that for resistors in series, all resistors have the same current capital I passing through them, as does the equivalent resistor, which means that we can, as shown here, use the same current I in Ohm's law for all the resistors. So that common current I cancels out, and we end up with this expression, which tells us that for two resistors in series, the equivalent resistance is just the sum of the resistances of the two original resistors. This holds in general. That is, for n resistors in series, the equivalent resistance is the sum of the resistances of all the original resistors. Here's another important case. A circuit with two resistors in parallel. In parallel means on one side of the resistors, a current capital I gets split up between the two resistors, and on the other side, the split currents I1 and I2 combine back together into the original current capital I. Of course, what we just said is an application of the node rule. I in equals I out for the junctions on either side of the two resistors in parallel. Let's simplify the situation. We want to replace this parallel combination of two resistors, R1 and R2, with a single resistor, REQ, that's electrically equivalent. Now, as we just said, the node rule applies here, which means the total current I through the equivalent resistor is just the sum of the split currents I1 and I2. Now notice for resistors in parallel, both resistors have the same magnitude of potential difference across the original resistors R1 and R2, as well as the same magnitude of potential difference across the equivalent resistor REQ. We can use this fact in Ohm's law to rewrite the currents like this. We can see that the common potential difference cancels, and we end up with this result. The inverse of the equivalent resistance is equal to the sum of the inverses of the resistances of the two original resistors. This also holds in general. For n resistors in parallel, the inverse of the equivalent resistance is equal to the sum of the inverses of the resistances for all the original resistors in parallel. We're now in a position to work an example of the analysis of a circuit with some complexity. We'll do that in our next lecture.